Here is a combined summary of the 2 pages. The authors propose a vessel-segmentation-based CycleGAN for unpaired multimodal retinal image synthesis, focusing on the image-to-image translation between color fundus, CF, and fluorescein angiography, FA, images. The goal is to generate synthetic multimodal pairs for training registration methods in a self-supervised manner, preserving vessel structures and transferring texture and style between modalities. Recent deep learning methods for multimodal medical image registration require large amounts of training data, which can be augmented using image-to-image translation methods. Conditional generative adversarial networks, CGANs, have been explored for CF and FA image translation, including Pix2-Pix-based approaches for aligned images and CycleGAN-based approaches for unpaired images. The authors extend the CycleGAN framework by integrating a vessel segmentation network, which serves as a shared representation between both domains. The proposed Vessel-CycleGAN method reformulates the original identity loss to learn the direct mapping between the vessel segmentation and the real image, and adds a segmentation loss term to ensure shared vessel locations between fake and real images. The vessel segmentation network is inserted prior to a UNet vision transformer generator network, and the method is applied to 2 datasets. The author's approach tackles the domain gap of vessels between both modalities, aiming to generate visually realistic images that preserve vessel structures. This is a crucial prerequisite for generating multimodal training data for image registration. By incorporating vessel segmentation into the CycleGAN framework, the authors propose a novel solution for unpaired retinal image-to-image translation, which can be used to synthetically augment multimodal datasets for deep learning-based multimodal retinal registration methods. Here is a combined summary of pages 3 and 4 of the research paper. The authors propose a novel retinal image synthesis method using a modified CycleGAN framework, dubbed Vessel-CycleGAN, which incorporates a vessel segmentation network to enable unpaired retinal image-to-image translation. The generator networks learn the mapping from vessel segmentation to the specific domain, rather than directly between the 2 domains. The cycle consistency loss, identity consistency loss, and adversarial loss are employed to train the network. The cycle consistency loss minimizes the difference between the real image and its reconstruction after passing through the cycle of applying both generator networks and the vessel segmentation network, as shown in equation 1. The identity consistency loss becomes modified to learn the aligned one-way image translation task of vessel segmentation, as shown in equation 2. The authors utilize the UNet VIT as the generator network and the patch GAN as the discriminator network. The vessel segmentation network is a 4-layer UNet, which is pre-trained for the vessel segmentation task. The CFFA dataset, consisting of 59 pairs of color fundus and fluorescein angiography images, is used for training and testing the synthesis method. The dataset is split into training, validation, and test sets, with equally distributed healthy and non-healthy eyes. For each training image, 9 512x512 patches are randomly cropped to 448x448. The HR fundus dataset is used to train the vessel segmentation UNet, and 81,484x484 patches from the CF images of the test set are used for the image translation task. The authors demonstrate the synthesis results in vessel segmentation overlays in figures 24, showcasing the effectiveness of their proposed method. Here is a combined summary of pages 5 and 6. The paper presents a retinal image synthesis method, Vessel-CycleGAN, which learns to generate fundus images from vessel segmentations. 2 tables, tables 1 and 2, provide quantitative evaluations of the proposed method and compare it with existing methods, including Pix2-Pix, VTGAN, and CycleGAN. Table 1 shows the results for the CFTOFA and FATOCF synthesis tasks using the CFFA test images. The metrics used are LPIPS, KID, and DICE, which measure similarity, realism, and vessel overlap, respectively. Vessel-CycleGAN achieves the highest DICE score of 0.9534 for the FATOCF task and the best LPIPS, KID, and DICE scores for the CFTOFA task. The experimental details are provided, including the training of the vessel segmentation UNet and the generator and discriminator networks of the retinal synthesis GAN. The paper also compares the results with CycleGAN and PIX2-PIX, which require aligned training data, whereas Vessel-CycleGAN uses unaligned data with randomly sampled patches. The results show that Vessel-CycleGAN outperforms the competing methods in terms of preserving vessel positions and achieving high dice scores. The qualitative results in figures 2 and 3 demonstrate the visual similarity between the synthetic and real images. The paper also tests the transferability of the trained models for CF images of the HRF dataset, where no ground truth FA images exist. The results show that Vessel-CycleGAN depicts fine structures, while PIX2-PIX and CycleGAN produce blurry results. The discussion highlights the novelty of the approach, which relaxes the unpaired image-to-image translation of multimodal fundus images to direct mappings from the vessel segmentation to the other modality within the CycleGAN pipeline. The paper concludes that the method can be used to augment training data for multimodal retinal registration methods and suggests future work, including the extension of the vessel-based approach to include optical disc segmentations and controlling the synthesis of pathological structures. Retinal image synthesis has been a crucial task in the medical imaging domain, with various approaches proposed to tackle this challenge. The existing literature highlights the importance of unpaired image-to-image translation, disentangled representation learning, and adversarial learning for synthesizing high-quality retinal images. For instance, Zhu et al. Introduced cycle-consistent adversarial networks, CycleGAN, for unpaired image-to-image translation, achieving impressive results in the field. Building upon this concept, Li et al. Proposed an unsupervised retina image synthesis method via disentangled representation learning, which demonstrated superior performance in generating realistic retinal images. Kai et al. Further extended this idea by incorporating triple multiscale adversarial learning with self-attention and quality loss, resulting in improved fundus fluorescein angiography synthesis. Recently, Liang et al. Presented an end-to-end retina image synthesis approach based on conditional GAN, CGAN, using class feature loss and improved retinal detail loss, showcasing enhanced image quality. Niu et al. Developed an explainable diabetic retinopathy detection and retinal image generation framework, which leveraged the strengths of both image synthesis and disease diagnosis. Torbanov et al. Introduced UVCGAN, a novel UNet vision transformer cycle-consistent GAN for unpaired image-to-image translation, demonstrating state-of-the-art performance in various image translation tasks. In addition to image synthesis, research has focused on diabetic retinopathy grading, such as the work by Hajeb Muhammad Alipour et al., which employed digital curvelet transform for accurate grading. Furthermore, Sindel et al. Proposed a keypoint-based vessel structure aligning network for multimodal retinal image registration, highlighting the importance of image registration in medical imaging. Budai et al. Presented a robust vessel segmentation approach in fundus images, which is essential for retinal image analysis. These studies collectively emphasize the significance of retinal image synthesis and analysis in the medical imaging domain, underscoring the need for continued research in this area.